Okay, this will be part 2, and I'm ready to turn the page on this. We just finished part 1. If you haven't seen part 1 yet, you should do it first. Makes more sense that way. We're now on page 24. There's some more bullet points on the reaction energy profile, topic 5.6. And additional information will be found in Unit 6, which we haven't done yet, but we need to get on that pretty soon. So, number 7, the diagram above shows the above on the left represents the reaction energy profile for a chemical reaction. The diagram on the right represents an incomplete reaction energy profile for a different chemical reaction. So when we're done, it'll look similar to the one on the left. On the diagram above on the left, write an R to indicate where the potential energy of the reactants, and P to indicate the potential energy of the products. So I'm going to put a R right there because that's where we start out. That'd be the reactants. And over here is P for the products. Draw a star to indicate the location of a transition state along the reaction coordinate pathway. Well, the transition state is where we're partway between reactants and products. That's going to be right here at the top of the hill. And draw a vertical arrow to indicate the magnitude of the activation energy barrier for the reaction. So that is from where we started to where we're ending, or at least to the peak. So that arrow represents the magnitude of the activation energy barrier for this reaction. Turning the page. Does the diagram show on the previous page on the left an energy profile of a chemical reaction that is classified as endothermic or exothermic? Justify your answer. Now, we haven't spent a whole lot of time talking about endo and exothermic, but remember, if it's endothermic, heat is, or energy is going into the reaction or into the reactants, so that overall the net flow of energy is in, so that we'll end up with higher energy at the end than we started with. And if it's exothermic, energy is flowing out of the process, so the energy of the products will be less than that of the reactants. And as you can see here, the final energy, potential energy, is lower in the products than in the reactants. So it is definitely exothermic. Products have lower activation energy than reactants. Oops. Heat is lost. All right, if you answered endothermic, complete the energy diagram on the previous page to show that it represents the energy profile of an exothermic. Wait a minute. If you answered endothermic in part B, complete the energy diagram to show that it represents the energy profile of an exothermic chemical reaction. If you answered exothermic, so whatever we had there, we have to draw the opposite. So what we need here is we need a hill and end up higher than we started. So now here's my reactants, here's my products. I'm going to draw a dotted line across here and a dotted line across here. And there's my activation energy, and there's my transition state. Number 8. 2 energy diagrams are shown above, with the major difference being the relative magnitude of the activation energy, assuming the constant temperature, which diagram 1 or 2 represents the reaction that should occur at a faster rate. Justify your answer. So what we're saying is we've got to go from energy here to energy here or here. All right, so clearly this activation energy is a whole lot lower than this one. E sub A is activation energy, by the way. So if it takes less energy to get over the hill, it'll go faster. We'll get over the hill faster. So diagram 1 represents, it's less clicky if I write in cursive. I hope you can read my cursive. A reaction with faster rate because of the magnitude of the activation energy is smaller. Okay, and I'm turning the page. If you need more time, you can always pause. All right, next, the equation above is known as the Arrhenius equation. K is the rate constant, A is the frequency factor, E sub A is the activation energy, which is normally reported. There you go. All right, I don't need to read all that to you. The Arrhenius equation is not included on the AP Chem equations and constant sheets. You will not be asked to do any calculations. However, it can be helpful to examine this equation in order to recognize relationships between the rate constant K and the activation energy, E sub A, and the reaction rate. So we're going to circle all the words to complete the following sentences. A relatively small rate constant, that's K, is associated with the relatively slow or fast reaction rate. Well, if it's a small rate constant, that means it's a slow reaction rate. Relatively large reaction rate constant is associated with the relatively fast reaction rate. A relatively small activation energy is associated with the relatively, okay, if it's got a low activation energy, it's going to get over the hill quicker. That'll be a fast reaction rate. A relatively large activation energy is associated with the relatively slow reaction rate. Increase in the temperature at which a reaction is carried out should increase the reaction rate and increase the magnitude of the rate constant K. Remember, if it's going faster, there's a bigger K. Decrease in the temperature should decrease the rate and decrease the magnitude of the rate constant K. It's important to know that if you change the temperature at which a reaction is carried out, this will not change the magnitude of the activation energy for the reaction. Okay, we just get there faster when the temperature is higher. It's easier to get over the hill. And if you look back at earlier, at the higher temperature, we had a greater proportion who have made it over the hill. That's what that means. We got to more have gotten past the activation energy barrier, E sub A. So that's what that's talking about here. Hope you're not getting carsick. Okay, and maybe we should stop here and upload this one as well. So let's stop right here, and then we'll be back in a minute with part 3.